Hello and welcome to our physical sciences session. My name is Temba. Today we are focusing our attention on something very exciting that has to do with power in the context of electric circuits. Right. Now, just a brief overview in terms of how the concept of power, falls into the knowledge area of, electricity and magnetism. So the context is electric circuits. By now, we are familiar with the Ohm's law that deals with the relationship that exists between current and voltage. Okay, and also we are familiar with the types of connections, the series, parallel, or a combination of the two. Right. So in the context of power, these are some of the the big thoughts or the big question that we want to pose from the onset, so that it guides our discussion for the purpose of today's session. Right. The first question says, what effect does adding identical light bulbs in series have on their brightness? So at the end of the day, we want to establish the effect of having more identical light bulbs, in series, and how that affects actually the brightness, right? And then the second question talks about the same effect. However, this is in a parallel connection. So these are the two main questions that will guide our discussion for today, right? Okay, so when it comes to the terminology, remember, definitions are a very important part of the language. So as we use the term power, it is in the context of electric circuits, right? So understanding the definition and being able to recall them is very, very important. So remember, the examination guidelines gives us what is acceptable in as far as the definition is concerned. Take note, keywords are very important, and these keywords must be used in defining in the correct context. Right, so what are some of the keywords? We've got power, we've got energy. Energy, that has a lot to do with work. But remember, the concept of power is also broad. We can talk about power in the context of mechanics, but here we're looking at it in the context of electric circuits. We'll also look at brightness as well as the Ohm's law. So these are the key ideas or key terms, right? So power is defined as the rate at which work is done. So remember, when work is done, energy is transformed from one form to another. Okay, so these electrical components, it could be a light bulb. What it does, if it does work, it means it transforms electrical energy into light and maybe some heat. Okay, but as it does that energy transformation, it actually does work. Right, and then the symbol for power is capital letter P. Do not confuse it with the small letter p for linear momentum, right? So power is measured in watts. So the watt is the SI unit of electrical power, right? Okay, now power is also related to the brightness of the light bulbs, okay? Remember, brightness is something that is very, very qualitative. You cannot quantify brightness. It's something that you look at it, and by comparison, you can say bulb A is dimmer, bulb B is brighter. Okay, so that's something that is qualitative. So we cannot quantify brightness, but this brightness can, to a greater extent, be an indication of the electrical power of an electrical component. Right. So let's say, for example, we can talk about a 40-watt bulb, which is less bright than a 100-watt bulb. So if something is less bright, we can, describe it as in terms of the term dimmer. So if something is dimmer, it means it is less brighter. Right. Okay. So when we talk about power, the formula is work per unit time, or work done per unit time, right? So work is measured in joules, right, when time is in second. So in other words, we are saying that a watt of power is a joule of energy transformed per unit time, which is equal to a second, right? Okay, so there are three formulae of power that we can use depending on what you have. These three are actually given in the data sheet. Just be able to identify them and know when to use them appropriately. So that we copy these formulae as they are and then use it in the calculations as they are. Right. Okay. So what do these formula tell us about the power relationship? Okay, one thing that comes to mind, so there's a practical method to measure power by using an ammeter and a voltmeter, okay? Because we know that P is equals to VI. So if we have the potential difference across a component and the amount of current passing through it, we are able to determine power, okay? So power depends on both current and potential difference. So for constant power using different resistors, potential difference is inversely proportional to current. This is how we actually show that. So if power is constant, then there is this type of a relationship between voltage and current. So the constant gradient in this case represents the power of a device. Right. So in the formula, P is equals to I squared R. When resistance is constant, right, we can immediately note that power is directly proportional to the square of current, right? This is the mathematical representation of this relationship. And then this constant gradient represents the resistance, right? Okay. Now, when resistance is constant, again, we can also realize that the power is directly proportional to potential difference squared. So if that is constant, we can actually derive this relationship. P is directly proportional to the square of potential difference across a component. And then this is the graphical representation of this relationship. Right. So these are some of the very important things in as far as power as a concept. And remember, it is in the context of electric circuits. We'll take a short break for now. When we come back, we'll explore a number of ideas around brightness of light bulbs within a series as well as a parallel circuit. See you after the break. Welcome back to our session. We're still looking into the concept of power, but now we want to turn our attention onto something that's very, exciting in terms of what we want to discover in as far as the relationship that exists between brightness, of identical light bulbs that are connected either in series or in parallel. Now let's look at the parallel setup first. Right. So we are saying that electrical power is related to brightness, and brightness is something that is qualitative. It means it's something that we can compare, but we cannot exactly quantify in terms of, numerical, in a numerical sense. Now the question is, what effect does connecting identical light bulbs, we assume, in series or parallel, have on the brightness? Now the internal resistance of the cells will be ignored. Right. Now let's put this on record. If we ignore the internal resistance of the source of energy, which is the battery or the cell, we are simply saying that the EMF of the cell is actually equal to the terminal potential difference. So in this case, there is zero internal resistance of the battery. Right. Okay, so we're going to set up a simple circuit using a 9-volt battery, a 3-ohm light bulbs, 3 of them, and we also have an ammeter and a voltmeter. So this is the setup in terms of this investigation, right? We want to find the effect of or establish the relationship between connecting identical light bulbs. These must be in series on the brightness. So in terms of the variables, because this is a scientific process, what is it that we're going to keep the same? These are our control variable. We'll use the same conducting wire. We shall try by all means to keep the temperature constant, and also the cell does not have any internal resistance. So the internal resistance of the cell is 0. Okay, independent variable is what exactly we're going to manipulate or change. We'll add the number of light bulbs which are identical, okay, in series, okay? will increase that number, right? And the dependent variable, or the response to changing the number of light bulbs, is actually the brightness of the bulbs in that circuit, right? So the hypothesis in terms of the guess, when more bulbs are added in series, the brightness of the bulbs increases or decreases. So this is a guess that we want to, at the end of the day, we must respond. Our findings or our conclusion must respond or answer this hypothesis. It's something that we want to establish. Right, so here is a setup that we're going to use by way of a simulation. Right, so we've got a 9-volt battery, a 3-ohm light bulb, okay? So there is no current in the circuit, right? So if we close that switch, there is a current of 3 amperes through the light bulbs, and we can observe the brightness of this light bulb, right? Now, what we're going to do next is to add another identical light bulb in series, right? And see how that exactly affects the brightness, right? Okay, so we'll add another 3-ohm. So the light bulb again is 3 ohm. Now what does that mean? It means these light bulbs are actually identical, right? Okay, so we'll connect that using a connecting wire, right? Okay. Okay, that's our light bulb there, okay? Then if we close that, you immediately realize that the current is half what it was, and the brightness of the light bulb has also changed, okay, without being specific as to whether it became brighter or, you know, dimmer, but there is an indication that the current in the light in the circuit has halved from 3 amperes to 1.5 amperes. Now, what do? We'll add another light bulb which is identical, also in series, right? So that's another 3-ohm light bulb. Remember, we said when they're identical, it means that they've got the same resistance, all right? Okay, so these are our light bulbs, okay? We've connected the 3 light bulbs now. You can immediately tell that there is a drop in the current. Now, as we added these identical light bulbs in series, there is a drop in current. What does that tell us in terms of brightness? We can immediately tell that there was indeed a change in the brightness. Right, okay? Now let's go back to our slide and continue with our discussion. It says, when more bulbs are added in series, the brightness of the light bulb actually decreases. In other words, they became dimmer. Okay, dimmer, it means less brighter, right? Okay, now we also want to look at the conclusion based on our findings. So the more bulbs we added in series, we realized that the potential difference stays the same across the light bulbs. Remember, EMF is equals to terminal potential difference. So there was a drop in current. Why did the current decrease? Because as we added more light bulbs in series, the total resistance increased, okay? Okay, so in series, as we add more identical bulbs in series, there is an increase in total resistance. Hence, there was a decrease in the brightness of the light bulb. So that was the conclusion. So the main question that we asked is, what happens to the brightness of the identical bulbs when we keep on adding them in series? We are saying that they get less brighter because there is an increase in the total resistance of the circuit while there is a drop in current, right? Now let's look at the effect of adding identical light bulbs in parallel on how it affects the brightness. So we'll set up a circuit using a 9-volt source, and we'll have 3 identical light bulbs, each of resistance 3 ohms. We'll also have, the other simple components that we need to set up a circuit. Okay, so in terms of the variables, because this is a scientific process, what is it that we're going to keep constant? We'll use the same conductors and try to maintain in some way the temperature, and we'll still use a battery or a cell with 0 internal resistance. So what is it that we're going to change or manipulate is the number of light bulbs in parallel, okay? So this is the number of light bulbs that we'll connect in parallel. And we want to see how that affects the brightness of the light bulbs, right? So the hypothesis that we want to answer at the end of this demonstration is we want to arrive at a solution for this following statement. When more bulbs are added in parallel, the brightness of the light bulbs either increases or decreases. So we want to arrive at a solution for that, right? So we'll use a simulation to set up the apparatus as shown in the circuit now, and then we can go on to change the number of light bulbs that are connected in parallel, right? So first of all, we've got that 9-volt source. There's a 3 ohm light bulb. All the light bulbs are 3 ohms. Hence, we are saying that they are identical. So the implication of the term identical, it says to us that not only are the light bulbs the same size, shape, color, and everything, but essentially they've got the same amount of resistance, right? Okay, so we will complete the circuit. You'd realize that now we can't have a single light bulb and say it's parallel to itself. So if we have a single light bulb, this is the brightness, there is the current of 3 amperes. Take note of that. Right, let's open that switch and add another light bulb in parallel and see how that exactly affects our brightness. So that's a second light bulb, okay, that we will connect, right? And then we will also complete that circuit and see how that affects the brightness. Right, you can realize now already adding another light bulb increases the magnitude of current, and then it looks more brighter in comparison to when we had only a single light bulb connected in series. Right, let's open that switch and then add the third light bulb in parallel and see how that affects the brightness of the 3 identical light bulbs. Right, okay, so that's another light bulb over there, okay, good. Okay, so we've got 3 identical light bulbs that are actually connected in parallel to each other, right? Now we'll complete the circuit by closing that switch and see the effect on brightness, but also take note of the magnitude of current, total current in the circuit. So that ammeter, we've placed it deliberately at that point to actually keep track of the magnitude of current in the external circuit, right? So if we close that, you see, now the current is 3 times the initial one, okay? Now it's even more brighter, right? Now let's go back to our slides and then, okay, the question that we asked ourselves is that when more bulbs are added in parallel, the brightness of the light bulbs increases, right? The brightness of the light bulb increases. What does that mean? It means the more light bulbs which are identical we add in a parallel connection, their individual brightness will increase. But also we can attribute that to, to the extent of resistance in the circuit, which would refer to as the equivalent resistance. So there's a drop in the total resistance which resulted in an increase in current. Now remember, power is about both current as well as resistance. So as there was an increase in current, never mind the current was split between the identical light bulbs. These light bulbs, at the end of the day, they become more brighter, right? So I think we've answered that question. But then in conclusion, we are saying that if we have more light bulbs in parallel, the potential difference stays the same. Okay, where does this come from? Remember, in any parallel connection, the magnitude of potential difference remains the same, whether the light bulbs are identical or not. In a parallel connection, potential difference remains constant. So that's a fact, okay? The current through each bulb stays the same, okay? But the total current increased. So we saw that initially we had 3 amperes. And then after that, the reading of the total current was 6 amperes. And then after the third identical light bulb, we had a current of 9 amperes, right? So indeed, there was an increase in current. So, but the total resistance, which is R parallel, there was a decrease in the total resistance. As a result, the brightness also increased. So we've managed to arrive actually at that conclusion. Okay, so in a nutshell, we are simply saying that, remember, power is not just about current, okay? And power is a combination of both potential difference as well as current. But remember, the combination of these two very important quantities, as we have demonstrated in the simulation, is that the more of these light bulbs we connect in series, effectively, what does that do? It increases the total resistance of the circuit, you know, because each light bulb is actually a resistor, okay? Then we asked ourselves that, do these light bulbs actually do work? Yes, they do, because they convert electrical energy into light and some heat. So as they do some form of energy conversion, they actually do work. So the power has to do with the amount of electrical energy that each of those light bulbs actually, you know, transforms into light, okay? The more work it does per unit time, the greater its power. Hence, we are saying that in a nutshell, power is a combination of both potential difference and you know, the current of a resistor, right? So in conclusion, we can also talk about, you know, the parallel one, because in a parallel, what is very important is that as you add more resistors in parallel, so this is actually what we had. If I can just quickly summarize that, right? So these are the identical light bulbs if I'm going to use symbols. Right? These are the three identical light bulbs. So in this case, we had the lowest effective resistance, which increased the total current. Because in this case, you'd realize that even though the current is split between the three light bulbs, but the total current in this particular setup gets higher and higher, as we would have seen in the values that we actually recorded during the simulation. Right. So we are simply saying that this experiment or this investigation that we have conducted, it serves also to try and remind us of what is important in as far as, you know, your scientific inquiry skills. You need to keep track of the data, you know, take note of what is it that we manipulated. And in both cases, we were changing the number of light bulbs, but there were two aspects to our investigation. We had a series as well as a parallel. So increasing the number of light bulbs in series, actually, we wanted to find out how that exactly impacts on the brightness of those light bulbs. So if we can go back to that first part, which talks about the series, and try and point out some of the very important things in this discussion, right? Okay. Right. So in the series, we are saying that ultimately we had a scenario where we had three identical light bulbs like that in series, right? Okay. This is the part of the circuit that we are interested in. Let's say, for argument's sake, that's R1, that's R2, that's R3. So each of these individual light bulbs, which are identical, they are resistors. So the total resistance in this case, as we would remember, is equals to the sum of those three resistances, okay? Then if we continue adding, there is an increase in the total resistance. So if resistance increases, right, the total resistance increases, right? If it increases, how does that affect the total current? It means the total current in the circuit decreases, right? Now the decrease in the total current affects the brightness. But remember, all the three light bulbs will receive the same amount of less current, which is the total current. Hence, they will be actually dimmer. So dimmer is another way of saying less brighter. Okay, so the argument, it needs to follow some form of some logic. Okay, so adding the three resistors in series increases the effective resistance of the cell. That results in a drop in current. Now, the amount of current, nonetheless, we need to indicate this, is the same for each of these three light bulbs. So at the end of the day, we can answer our guess and say, yes, indeed, we projected that if we add more light bulbs which are identical in series, at the end of the day, they will have less brightness, or they will be much dimmer. So that's how we managed to arrive at that. Okay. Welcome back to our session. We're still talking power in the context of electric circuits. Now we want to look at, some of the discussions or the thinking behind, the effect of resistance on power in a combination of parallel and series circuit. Right. Now, the question that we want to focus our attention on is, it says, what effect does an internal resistance in a battery have on the brightness of light bulbs in a circuit? So the internal resistance of the battery now will not be ignored. What does that mean? We are saying that the battery has got some EMF. However, the EMF is not going to be equal to the terminal potential difference. Why? Because we are saying that within that battery there is some lost volts due to the internal resistance of that battery. So this is different from what we focused on in our earlier discussion, to say that we are going to ignore the effect of internal resistance of a battery. So in this case, we do take into account the internal resistance of the source. Right. Okay. So if we increase the resistance of the external circuit, so the effect of internal resistance on a battery is that it will increase the resistance in the external circuit. Remember, the battery is actually in series with the external resistance, right? So if, say, for argument's sake, that's R, we are simply saying that if this is part of the circuit, the effective resistance in the circuit will be R plus R, as we have represented it in that way. So it's like if we consider the internal resistance of the battery, which is in series with the external resistance, then the effective resistance of the circuit will actually increase. Right. Now, increasing the effective resistance will actually decrease the current passing through the battery. Right. So if there is an increase in current, we also know that the lost volts will decrease. Right. So with V internal, which is the lost volt, will decrease, right, while the external resistance increases. So from the equation, E is equals to V external plus V internal. We are saying that if we take into account the internal resistance of the battery, the effective resistance of the circuit is going to increase, right? When that increases, it means V external increases while there is a drop in internal resistance. You need to take note that for E to remain constant, if V external increases, then V internal or loss volts must decrease because E remains constant, right? Okay, now if the decrease in resistance of the external circuit, this is what is actually happening, will actually increase the current passing through the battery, right? So the lost volts or the V internal will increase while the external voltage decreases. So I think we get to a certain point where we appreciate that an increase in lost volts actually results in a decrease in external voltage because E or EMF must remain constant. So the opposite is true. If the lost volts decrease, V external must increase. Okay, right. And then what effect does an internal resistance in a battery have on the brightness of bulbs in a circuit? Right. Now we want to look at the effect of considering or taking into account the internal resistance of the battery on the brightness. Remember, if we add the internal resistance of the battery, we're actually increasing the effective resistance of the circuit. And then now we want to establish exactly how that actually affects the brightness of the light bulbs in the circuit. Now, we'll use this circuit as an example, okay? We want to know what effect does the internal resistance of the battery have on the brightness of the light bulbs. Now the assumption is that the three light bulbs, 1, 2, and 3 are actually identical. Take note, switch S1 is open, right? Okay. Now all the 3 light bulbs are identical. The meaning of identical is that they've got whatever the resistance they have is the same for the 3 of them. Now the question is, explain what happens to the brightness of the bulbs when switch S1 is closed, right? We are going to close switch S1, right? But before we close switch S1, as it is, if bulb 1 and 2 are identical, right? We are saying that they receive the same amount of current. And when that happens, it means then they have got the same brightness, right? But if we close switch S1, we want to establish how will that affect the brightness of the 3 light bulbs, right? So before S1 is closed, we have already gone through that. We're saying the current through and the potential difference through the bulbs is the same, right? Okay, because these 2 are in series, right? Before we close switch S1. And then bulb 1 and 2 have the same brightness. This is before we closed switch S1. So in other words, current through bulb 1 is equals to current through bulb 2 when switch before switch S1 is closed. This is what we have. So they've got same brightness, right? Same brightness. Very important. Right, okay? And then closing switch S1, what does it mean? Okay, now we want to appreciate that bulb 1, okay, let's call it R2, which is bulb 2, and R3 are connected in parallel, right? They are connected in parallel to each other. And both of them are actually in series with R1. So all the current passes through R1. And the total current is split between bulb 2 and bulb 3. And actually, they receive the same amount of current. Right. So that's the thinking that we're going to use. Now, after S1 is closed, what do we appreciate that there's a decrease in the external resistance of the circuit. Okay, why? Because we are adding resistors in parallel. So this is due to adding resistors in parallel, right? That's a fact, okay? And then also the current through the battery this is the total current. The current through the battery and bulb 1 increases. So this is the main current. There's an increase in main current due to a decrease in the resistance, right? Furthermore, internal voltage increases and V external decreases. We spoke about this relationship. There's an increase in internal resistance and a decrease in what? External voltage. Why does the external voltage decrease? Because the external resistance is decreased due to adding more resistors in parallel, right? Okay, so the V external is equally divided between bulbs 1 and the bulbs in parallel, which is actually bulb 2 and 3. In other words, this statement suggests that V across R1 is equals to what? V across R2, okay, which is the same as V across what? R3, right? Why? This is a parallel connection, so V remains constant. Okay, so the external voltage is actually divided across the 3. So in other words, this V parallel, if we can add a V parallel here, okay, and then we know that there is a V1 across that light bulb 1. So that will give us the total V external, which is V external in this case is equals to V parallel plus V across R1, right? Okay, and then also we know that the current through bulbs 2 and 3 divides equally. Then it means the current that goes through R2 and R3 is the same but less than the current that goes through R1. Okay, so as a result, we are saying that these 2 bulbs will actually be dimmer, your R2 and R3, and of the same brightness. So the brightness of bulb 2 and bulb 3 will be the same, but it will be dimmer compared to that of R1. Right. Okay, so in conclusion, we are saying that before S1 is closed, bulb 1 and 2 have the same brightness because it was a series connection. Okay? And remember, these light bulbs are identical, very, very important. But once we closed S1, bulb 1 is similar brightness as before, okay? But bulb 2 is less brighter than bulb 1. However, the brightness of bulb 2 and bulb 3 is actually the same because these are identical light bulbs and they receive the same amount of current, right? So that's the relationship that exists between, you know, the brightness in a combination of a series and parallel circuit. For now, we'll take a short break. When we come back, we'll look at more in terms of calculations of power in the context of electric circuits. See you after the break. Welcome back to our session. We're still looking at power in the context of electric circuits. Now let's take a turn and look into, you know, some of the calculations that are based on circuit problems. Right. Take note, the formula sheet becomes a very, very important tool, and also try and pay careful attention to the mark allocation as to whether the question concerned is a routine calculation. You know, it requires simply your formula, your substitution, and the answer, which includes the correct SI unit. And then if it's a multi-step type of a problem or a calculation, it will have at least, you know, 4 marks or so. So pay careful attention to that. Let's look at those practically. This is just an example of, you know, some of the type of problems that you must expect in as far as circuit calculations. Right. Okay, the first question that we have, we've got 3 electrical devices, X, Y, and Z, that are connected as shown. So this is a typical circuit. So from this circuit, we can immediately, you know, extract some of the very important information in terms of the EMF, which is given, in this case, it's 24 volts. Right, and also we can immediately extract from the circuit that the internal resistance of this circuit is unknown. So if R is unknown, we cannot assume that the battery has negligible internal resistance. So what this suggests to us is that the battery does have some internal resistance. However, it is unknown, which is not a trace mesh either way. Right, okay, now, so we are told that with switch S1 closed and S2 open, the devices, they actually function as rated. So the question that follows is that calculate the current in component X. Now in this case, we have closed switch S1 while switch S2 is open. Now, let's carry out our calculation that has to do with determining the magnitude of current in component X. So we can close that switch there, okay? Now we want to establish how much current passes through component X when switch S1 is closed. So it's very important at this point in time also to try and interpret what that means in terms of closing switch S1. So if switch S1 is closed, in a nutshell, what are we saying? We are saying that the only 2 components that are in the circuit is actually X and Y. Z is out of the circuit. Why? Because the switch that connects Z to the entire circuit is actually open, which is switch S2. Very, very important piece of information. Right, so we want the current through X, but what do we know about X? Let's extract the information. We've got the power rating of X, okay? The P of X is equals to 100 watts, right? And then also the potential difference across X, which is V of X, in this case, is given to be 20 volts, right? Now, what are we looking for? We're looking for the current that passes through resistor component X. So if we've got P and V, we are able to find the current. So P is equals to V times I. So this is the formula that we identify in the data sheet. So very, very important, again, as a reminder, if a question requires a calculation that involves you identifying the correct formula in the formula sheet, always copy the formula as it without trying to manipulate or change the subject, because in this case, we're actually looking for current. Right, so we've got the P, which is 100 watts, okay, is equals to the voltage, which is what, 20 volts. Then we're looking for I. So I think it's a simple return calculation. This is 20 divided by 100 divided by 20, which is actually equals to 5 amperes, right? It is equals to 5 amperes. So that's the current that passes through X, right? So it's a routine calculation, formula, substitution, and answer, right? And then the follow-up question. Now, switch S1 is still closed, and then S2 is still open. So for argument's sake, we're gonna close that switch once again, and then these devices, they actually operate as rated. Now the question wants us to calculate the resistance of Y. So in other words, in terms of notation, we'll use resistance of Y. This is what we want, okay? Right, okay? So if S1 is closed, okay, we want the resistance of Y. What do we know about Y? We were looking for resistance of component Y, which we do not know, right? What do we know about Y? We know that it has a power rating of 150 watts, okay? 150 watts. And then there is something else that's very important about component Y, which we can also extract from X. It means that we need to realize that component X and Y are actually connected in parallel. And exactly what do we know about a parallel combination of resistors in a circuit? That the potential difference remains constant. In other words, we are saying that V of X is equals to V across Y, right, which is equals to 20 volts, right? So we are looking for the resistance of Y. So we can use the formula P is equals to V squared over R. So that's the formula that we copy from the data sheet, right? So we've got the power, which is equals to 150 watts, okay? Divided is equals to 20 squared, okay? 20 squared divided by R. So if we were to make R the subject, we'll get R is equals to 150, or 20 squared over 150, which is like 400 divided by 150, right? Then R of Y is equals to, we can quickly go to our calculator and verify that, right? So what do we have in this case? We've got 400, which is 20 squared, okay, divided by 150, which gives us what? That's the value there, 2.67, right? So this is 2.67 ohms. That's the correct SI unit, right? And then also we are called upon to calculate the internal resistance of the battery, right? Now, we are looking for the internal resistance. We've already indicated that the internal resistance is not given, right? Now, if we've got so in this case, we're looking for the internal resistance of the battery. Now, we've got the current, okay, through X, okay, which is equals to, I think we got something like 5 amperes, right? Now, if we can find the current through Y, okay, we are able to determine the total current, right? So if we are to find that current, so in terms of Y, we are saying P, if we say P is equals to VI, okay, for argument's sake, this is one of the many methods that you may try and use. So now we are talking about Y, right? Okay, we're talking about Y. So this is 150 watts, okay, is equals to 20 divided, multiplied by I across Y, okay, through Y. So our current through Y is equals to 150 over 20, right? Okay, so if we can clear that, okay, this gives us 150 divided by 20, right? Which gives us what? 7.5, right? This is 7.5 amperes. 7.5 amperes. Now the total current through the battery in this case is 5 plus 7.5, which gives us what? 12.5 amperes. Okay, 12.5 amperes. That's our total current. But then the question wants us to determine the what you call the internal resistance of the battery. There are many ways to do this. Now we know that V external is equals to 20, right? So our V external is equals to 20, right? It's equals to 20 volts, right? Because it's just these two in parallel, right? Now then V internal will be the difference, which is equals to 4 volts, right? Now what do we know at this point in time? We know that V internal is equals to the main current multiplied by the internal resistance of the battery. So we've got V internal, which is actually equals to 4 volts, right? Then the total current in the circuit is 12.5 amperes multiplied by R. So in other words, R, which is the internal resistance of the battery, if we can just quickly confirm that by means of a calculator, we have got 4, okay, 4 divided by 12.5. Okay, this gives us what? 0.32. So that's the internal resistance of the battery, which is 0.32 ohms. Right. So this obviously this question involves us actually getting the total current. And how exactly did we get the total current? We managed to say the main current that goes through the battery is actually split between X and Y. So if we have an understanding of how much current goes through X and we get the current that goes through Y by way of calculation, then we are able to get the total current which goes through the battery. And then if we know the external voltage is 20 volts, then the internal volt will be 4. Then as a result of that, we are able to determine the internal resistance of the battery. Last but not least, we are told now that both switches are closed, okay? Now, and also, if with switch S1 closed and switch S2 are open, the devices, they function as rated. So the power rating of X and Y do not change. So the current reading in the ammeter is still 12.5. Remember, this 12.5 is our total current, right? Now, we are told that if we close switch S2, now switch S2 is closed and then the total current remains constant. What does this tell us about resistance of Z? Right, now let's look at this. Both switches S1 and S2 are closed, right? And then we know that the main current is actually equals to 12.5 amperes, right? Now, if Z is part of the circuit, what is actually happening if this current remains constant? What does it tell us about Z? Okay, or rather about the resistance of Z. Remember, the more resistors we add in parallel, we're actually decreasing the effective resistance in the external circuit. So if the current, which is the main current, the total current remains constant, it simply means that by comparison, a component Z is actually very high resistance, such that there's very little current or no current passing through it. Now it tells us that, okay, then this component Z could actually be a voltmeter. Okay, because if this current is to remain constant, and then because we have included Z, it means Z is actually a voltmeter. Why are we saying it's a voltmeter? Because it is a high resistance which effectively did not decrease the total current in the circuit. So these are some of the examples that you want to think of when it comes to solving circuit problems. But a lot of practice would most definitely go a long way in terms of trying you to, to get you to understand these scenarios. With that, because of time constraints said, we'll just sum it up and say, with more practice, I think you get more comfortable in as far as these questions are concerned. From myself, from now, see you next time.